ladies and gentlemen, to SPS IPC Drives 2013. The next presentation you're going to see is the English version of the TIA portal and the engineering efficiencies that we have in the standard tool sets. Ultimately, what you're going to see on the stage today is how to save time or money during your daily operations from more of a service use case perspective. For the first time, something we haven't shown is the network architecture, or something called topology view. All right, let's give focus to it. And so what is it? Essentially, every single connection from every single device, the first P1 to a P2 of device 1, device 2, we know all the interconnections on Profinet. So what does this give us? This gives us physical layer diagnostics for the entire network architecture directly in the engineering tool. All right, let's go online with it real quick, and let me show you what I mean. You'll know that. You get the orange bars across the top, so we are online with this actual project. And you can see the check marks and all the Profinet cables are highlighted in green. So for instance, if I come over to this drive real quick, let me pull out Profinet cable, and you'll see that we have a network failure directly between the switch and that drive. That means if a tow motor was driving through here and knocked out a cable tray, you could go to the engineering tool and immediately find the network failure just like that. Solve your problem, get up and running, and mitigate the downtime. Problem solved. Trying to create engineering efficiencies in your daily work. That way, you can mitigate downtime in a service event, okay? So we've seen the network architecture, we've seen the hardware architecture, everything up here. Let's get this system up and running. So you can see from the comfort panel, we have something called Smart Access. That's how we're able to visualize this up here. And let's go back to the home position real quick. Get them up and running, turn power on, and go down to home position. Okay, so if we get the model running, let's see what happens. So it's kind of herky-jerky, something's wrong here. Well, let's go back into the software and see if we can figure out what's going on. Let's go back online real quick, and you focus the CPU, go online real quick. The orange bar across the top, and now you see we have some green bubbles here in the tree structure, but I noticed something right off the bat. You see one of them has a blue and orange bubble. So what that literally means to me automatically from a visual standpoint is there's something online, offline is different for that particular block. Let's investigate further. Let's give focus to the CPU, and let's look at all the software components. Go to compare, online, offline. So now we're going to have a visual representation of all the software components for this entire project at this point. And for that matter, we could even filter. That way we could find individual problems, online, offline. So let's use the filter button. There's that FB1 again. We can still see there's a problem there. Now if we want to investigate even further, we can go directly into that and look at the physical code in the blocks. So let's actually go do that now. You're going to see it, I believe it's SCL. Yep, it is SCL for online, offline. And now if you want to find the next potential difference between online and offline, we can use that icon. Let's go to find it. There it is. So we have a multiplication of a 1.25 for the online program. I know for a fact that's not correct. I wrote the program. The offline is the master. So we've had some kind of unauthorized access and change of this program to solve a problem. Well, that's not what we want for this particular application. So let's go back and let's actually choose download to device. Let's execute it. Now it's going to compile the fact that we made this simple change. You'll see that we have this consistency download here. And what this means from the old generation to the new generation is the new generation, we do the consistency download in the software, not in the hardware like we used to. So let's choose load. Now it's going to load to the 1516, and we'll click finished, and we've solved our software issue. Okay, so since we had an unauthorized access, I want to make certain this doesn't happen again, right? We saw we clearly had some problems. There was some jerk in it. Well, we can actually add something called level 4 protection. Let's give focus to the actual CPU. Or we can show the know-how protection too. For instance, something different in our know-how protections, we have the ability to protect not only a single block, but the entire program. So if you're only concerned about the algorithm in one block, you can protect that block. Or if you're concerned about the entire process, you could highlight all and protect the entire process. So for instance, once you give focus to that particular block or the program, you click protect, add your passwords in, the block's locked down. You also have something called copy protection. The 1500 has to use a memory card. So what does this mean? We have the ability to bind the program to the serial number of the memory card, or you could bind the actual program to the serial number of the CPU, whichever you want. That way, somebody pulls that memory card out and you bound it to the CPU, guess what? They can put it in a different CPU, it's not going to work. The program blocks are not there. All right, now let's actually do the access protection side of this. Give focus to CPU, click properties. You're going to notice down here at the bottom we have the protection level, and we see we have multiple levels available to us. The new one is this level 4 or HMI access protection. If we give focus to that, we have to give it a password. Of course, you have to confirm that password. Now let's say OK, and let's download to the controller. It's going to compile the fact we've added the password. And you see stop all, click on load. Of course, we've made an actual change, right? This password protection is an actual change to the program. Click finished, and now we've protected our CPU and changed the program. Let's do a trace. How about that? Let's do something where we can look at actual variables coming from the drive and see if we can't figure out what's going on from the mechanical side. Well, if we go into trace real quick, we have the ability to have essentially an oscilloscope directly in the engineering tool, and you could even set this up if you have some kind of intermittent problem. Go away. You'll look at the variables you want to see if the trigger occurs. You could download this or view it actually. You could even download it to CSV file. That way you can solve your problems online or offline. If we give focus to that trace, we can actually go look and grab an individual predefined trace and load that in. So if you have multiple different types of traces you would like to use for a given potential problem. And in this particular one, you see we have a set position, a current position, speed, and access error. Those are our variables we're going to look at. The sampling, you see it's for every one cycle, 100 milliseconds, we're actually going to make a sample for exactly 6 seconds. And our trigger, we're going to do 4 seconds before 1,000 samples. So we'll know before and after whatever the event is. Okay? All right, so let's give focus to the controller or trace, go online. Orange bars across the top again. Let's move it into the online mode, say OK, and you can make it active. You could have multiple traces, up to 4 in a 1500 controller. And now we're starting to trace something. So let's go over here, turn it on, and let's go back down to the home position. And let's go up to the top and see if we make it. So everything appears to be fine. Let's give it one more shot, see if we have any problem. Okay, so there is a problem still. All right, so we should have a trace now. Oh, perfect. There's a full set of analytic tools directly in the trace capability. You have the ability to look at every single data point if you want to. You can look at delta time, delta amplitude. You can zoom in and look at individual portions of that trace, as he has done here. You can clearly see the green line is where we're supposed to be. That's the position. The red line is the actual position. So you see some deviation here, these steps. The blue line is the speed. So every single time we have a deviation, the speed tries to ramp up to catch up. So something mechanically is going on here between, let's say, for instance, the encoder, the technology module. It could be a connection on the shielding. It could be the encoder itself. We get our mechanical guy. He goes in. He solves the problem on the encoder side. Get up and running. And away we go, right? Other diagnostics we could give you. The new diagnostic concept from the TIA portal and the 1500 controller is we've actually moved the diagnostics to the firmware level of the controller. So what does this mean? This means that the software blocks are now not required. The diagnostics are at the firmware level. So you don't have additional soft blocks required to do diagnostics. This also means that even if the CPU's in the stop mode, you can see the diagnostics, solve the problem before you start the machine up, and don't create a problem during the machine startup. Well, also, the drive, since it's integrated, we have diagnostics for it as well. Not just the I/O, the drive in this particular Profinet example. This potentiometer right here, we've got it set up to be an overload condition. So, for instance, you'll see automatically that we didn't hit our position. So there's an axis error because it didn't hit the final position it was supposed to go to most recently. The diagnostic indicator in the top right-hand corner is turned red, and there's a wrench. If we give focus to this, we'll go automatically to the message, and we'll clearly see that there is obviously something motor overload condition for this particular drive. And I can even see the part number, exactly where it is in the Profinet architecture. And in fact, I can see some potential reasons on how we can solve this particular issue. You may notice something as well. I use swipe technology on this panel. That's something new we're doing from a functional capability in our panels. That way the user can use it the way they think would be most intuitive. Let me solve our problem. And how about this UPS? So we showed you even the drives have diagnostics coming into our portal and the ActiveX controls on our panels. How about this UPS? It's on Profinet as well. Well, we can get diagnostics out of him just the same way. So for instance, if I come over here and pull the handle, you'll see that the battery connection to the UPS has failed. There's no doubt that's correct. I'm holding the connection in my hand, right? Well, also we have the ability from the new diagnostic concept to have this not only in the ActiveX control in the diagnostic viewer up here on the panel, we can also have it on the display on the 1500, and we can have an engineering tool as well as on the web server. So you don't have to have a panel to see these diagnostics. Display or here, you can see it essentially for free, right? It comes with. If we just go into this actual web server, you can clearly see there is an error. There's no doubt. The photorealistic view of the 1500, go to module information, dive down through the Profinet architecture, find the UPS, click on it one more time. You'll see that it created a maintenance demand the moment that it realized this was gone, and then it created an actual error, the fact that the connection to the battery was interrupted. Correct. I can prove it. It's in my hand. So let's go solve our problem, replace our battery, whatever the case may be. And that means even the power components that are powering the system are integrated from a diagnostic concept. Not only the drive, but even the power side. Everything we can possibly give you, that way you can mitigate downtime, create engineering efficiencies in your daily work. That's what we're trying to build into the system. Okay, so we've shown you all kinds of diagnostics. We've shown you all kinds of user tools to help solve problems. Something else that we want to show you from an engineering standpoint. For the first time, we're showing the fail-safe 1500 controller here at SPS 2013. So for instance, how can we easily integrate that into our current project? Well, if we go back and give focus to the PLC2, you'll clearly see this is a standard CPU. There's no yellow bar across the top to indicate that it is a fail-safe controller. It's quite easy to change this into a fail-safe controller. Just give focus to it, right-click, choose Change Device. The pop-up gives you the opportunity to find another like device. Go find the fail-safe controller, have a side-by-side. If we click OK, you're going to notice automatically we get the yellow bar across the top. Once it updates, there it is. Also, you'll notice in the tree structure, we've automatically added the safety administrator, including other fail-safe blocks required to do a fail-safe program. If we give focus to the safety administrator, go to the F runtime group, you see that this has been added. So in order to actually run a fail-safe program, it's automatically been added into the program. And in fact, if we actually go to the main FB1 fail-safe, open up the instructions, grab the e-stop, that's been added now, and the other safety instructions, drag it in, accept the default data block. You'll notice even the code side is highlighted in yellow. So you'll know instantly everything that's standard and fail-safe by the designation of yellow in it, whether it's code or hardware. Well, I certainly appreciate your time today. If there's anything that you'd like to know more about that you see in this presentation, please don't hesitate to go ask some colleagues here at these kiosks or back in the booth. There's been several new things we've shown you. They would love to answer your questions. I certainly appreciate your time. I hope you have a good day. Bye.